Thank you very much. A survey talk such as this usually involves a certain amount of potted history where you take some liberties with the development for the sake of a good narrative. Now, that's a bit awkward when so many of the principals are in the audience. So I'm going to have to beg their indulgence if I oversimplify or rearrange some of their contributions. All right, so there's a new connection between logic and topology in the form of an interpretation of Martin Löw's constructive type theory into homotopy theory. So the interpretation has the character that the formal language is interpreted in terms of homotopy, spaces, continuous functions, homotopies, and so on, and logical constructions and formulas receive a meaningful, homotopically meaningful interpretation. Formulas become statements in homotopy theory. And then formal proofs in the system become true statements in homotopy theory, that is, theorems. So that's the nature of this interpretation. So in particular, you can use homotopy to construct models of systems of constructive logic and do things like show that a statement is not formally provable from the system by exhibiting a counterexample under the homotopical interpretation. Because after all, if it were provable, it would be true. Maybe even more interesting, you can use the constructive type theory as a kind of formal calculus to reason about statements in homotopy theory. And now one of the things about constructive logic that has really driven the development over the last couple of decades has been the fact that it has an implementation in computational proof assistance. That is, it lends itself to using the computer to check and even find proofs, formal proofs in the system. So now given that and given the homotopical interpretation, that opens up the possibility of having formally checkable automated proofs in homotopy theory, right, under this, combining these previous two steps. And in fact, given this interpretation, we even have, as always when you get a kind of connection between two different areas of mathematics, the possibility of transferring some ideas back and forth. So one thing that's happening now is some homotopical ideas are flowing into the logical system in that direction, and there's even a chance of things flowing in the other direction, that we might have some new homotopical methods based on ideas coming out of logic. And the combination of all of these aspects is what's being called the Univalent Foundations Program. It combines all of these things into a new program for the foundations of mathematics, and in particular it involves a new principle of reasoning called the univalence axiom. And by the time we get to it, then this is in fact an outline of the talk. So these are the things that I'm going to be explaining. Good. Okay, so let's get started. We can't get very far without saying what type theory is. So I'm going to give you a thumbnail sketch of what the Martin Löw system of constructive type theory is. It consists of different kinds of things. So on the one hand, there are the types, and I've indicated them here with some letters, and then there are constructors out of the types, so that if I have two types, I can make a new type, the product type, or I can make a new type here, the function type of those two types. And then associated to each type, there are the terms, and among the and I write that like this, a term and then a colon and then a type. That means this term has this type. So there are variables, there may be some constant terms of given types, and then associated with the type constructors, there are term constructors. So for example, if little a is a term of type big A and little b is a term of type big B, then pointy brackets a comma b is a term of product type, and we think of this, of course, as the pair a comma b. So the type a cross b is the type of all pairs of terms, one from a and one from b. And then the function type involves this notion of lambda abstraction. The lambda abstraction simply means if b of x is a term of type x, and the x, is a term of type b, and the x is a variable of type a, then lambda x of b of x indicates the function which takes the argument x to the value b of x. So it's just a formal notation for function abstraction or function specification. Okay, so that's the basic ingredients of the lambda calculus. People are already looking a little confused. The idea is we're specifying certain objects and at the same time keeping track of what kinds of objects they are by typing them. And the objects are arbitrary to start with, and then we can build pairs of them and functions between them. And we use this typing system to keep track of what kinds of objects we're building as we go along. Okay? Now there's one more ingredient in the type system, and that's this notion of type dependency, one more kind of basic ingredient. And the way you think of it is this. You think of it, so don't worry about the turnstile. This is purely conventional notation. What I'm saying here is if I have a variable of type A, I might build a new type here that involves that variable. And I think of this as a family of types parameterized, right, in this variable over this other type. So we think of this thing as a variable family of types where it's varying in a parameter coming from another type. That's what this notation means. So given such a family, I have some type-forming operations. I can take the sum or disjoint sum or coproduct of all of the terms in the family there, types in the family, and I can take the Cartesian product of the family. So those are kind of some basic operations on families that you're already familiar with from families of sets. And there are associated term-forming operations that are the expected ones. I'm not going to go into that. And then finally, there are some equations among terms, for example, of the same type. And these are very simple equations of the obvious sort, like if I take a pair and then I project out the first component, then I get that first thing back out. So there are some simple equations of that kind that I won't be mentioning further. So then we have a formal calculus of these types and these typed terms and equations among them, and we reason formally by rules of inference about these things that we're constructing. That's the idea of the type theory. It's usually presented as a deductive system with formal rules of inference, above the line and then a horizontal line and then below the line. That's just the conventional way of presenting this sort of a system. It can be presented in other ways. Vladimir has given us some lectures about other ways of presenting type theory. It was originally developed, as I said, as a foundation for a constructive style of mathematical reasoning, a kind of alternative to Zermelo-Fraenkel set theory, which has a special constructive character, which I'll be saying some more about as we go along. Pardon me? Which are the statements? So a statement, for example, would be something of this form, which is an equation, or something of this form, which says that this is a type with these variables. So it would be statements of that form. All right. Now the system has a curious dual interpretation that I want to emphasize. On the one hand, we think of these as mathematical objects that we're building. The types are like sets of some kind of constructive character, and the terms of the types are elements. And we're constructing these things as we go along. We're constructing the elements in the corresponding sets as we go along. On the other hand, there's an interpretation according to which the types are propositions, statements in the language, and the terms are proofs of the corresponding propositions. So here we have a kind of logical interpretation, and what were before constructions are now derivations of proofs of propositions. And that's a kind of odd feature of the system, but it's something to be aware of, and I'll explain it a little bit more as we go along. So here, just for example, this Cartesian product, as regarded logically, is a conjunction of two propositions. And the idea is simply this. If I have a proof of the proposition A and a proof of the proposition B, what should be a proof of A and B? Well, it should be a proof of A and a proof of B. So it's the pair consisting of those two proofs. Similarly, and this is where the constructive character comes from, I think of this sum operation as a kind of existential quantifier over this family. Well, first of all, a family is a family of types. So a family of propositions is something like a property or a relation or a propositional function, right? It's a proposition varying in a parameter. And then the disjoint sum here is like an existential quantifier. That is, it says there exists something of type A, namely X, which has the property B. Okay? And the rules are the rules for this operation are formally identical to the rules for this operation, as long as we read this operation in a constructive way. And what that means is, if I can prove that there exists something, A, that has the property B, then I better be able to give one which has that property. That is, actually exhibit something of type A that has the property B. And as long as I read things in that constructive way, the rules for these operations are formally identical. And that's what gives rise to this so-called Curry-Howard correspondence. The formal rules for type constructors, given by the usual rules for function spaces, Cartesian products, coproducts, and so on, are formally identical to the logical rules of inference for this fragment of logic, which is called the predicate calculus, the calculus of quantificational logic. Okay? So I'm going to have an example of this later on if it's confusing. Yes, it's a constructive calculus. Yep. So this is what gives the system its constructive character, which is what I'm trying to emphasize here. All right. So as I just said, according to the logical interpretation, we have these types representing, well, propositional logic of or and if-then. And then we have this predicate logic, that is thinking of these dependent types as predicates and relations, and thinking of these operations as the quantifiers for all and there exists. And so from the logical point of view, it's natural to add an identity relation on each type. So for each type A, I'm going to have a primitive relation of identity between terms of type A, and it says X and Y are identical. So it's a proposition that we can read that way. Okay, that's a perfectly reasonable extension of the logical system. However, now this begs us to answer the question, what does this mean mathematically? In order to preserve that correspondence that we had going between the Curry-Howard correspondence, between a mathematical and a logical interpretation. So on the mathematical side, there has not until recently been a good answer to that question, and I think the one way of understanding the progress that we've made with the homotopical interpretation is we've found a mathematical interpretation corresponding to this logical operation of the identity type, a so-called, I'm saying here, a geometric interpretation. More specifically, it's a homotopical interpretation. Yep.
I could interpret all of this just in set theory.
Yes.
And then the identity type would be 0 or 1.
It would be 0 or 1,
Yeah,
precisely.
That's the non-constructive.
That's a non-constructive interpretation, which would certainly validate all of the laws of constructive type theory and more, and many, many more that we don't want to validate because it would lose the constructive character of the system. Yes?
When X and Y are rules in the system,
Yes?
what does it mean by identity type A?
So logically, it means that they're proofs which can be treated as identical from a logical point of view. They're not the same proof, but maybe one interpretation would be they can be transformed one into the other by some series of transformations of proofs. Okay? So it has a kind of logical meaning, a proof theoretic meaning, and the question is, what does it mean mathematically? And that's what we're going to try to find out. Sure, yeah.
Well, actually, this is something which probably you would explain this nicely in terms of, but from my point of view, one of the key things is that not every type is an opposition.
Yeah.
That's one of the key things which makes everything so interesting.
Yep.
And propositions are defined as types for which any two objects or any two terms are existent. What it means to be a proposition is to satisfy the property that any two terms are existent. So any two proofs are existent.
Okay. Let's push ahead. So I want to now analyze this identity type and find an mathematical interpretation for the identity type. So we have to look at what the rules are for the identity type, because that's what we need to model. So here are the rules for the identity type. There's an introduction rule which says that for any term A of type A is identical to itself, and here's a canonical proof of that statement. It's like a reflexivity proof. Fair enough? The elimination rule is a little bit more of a mouthful. It has this formal form here, but you can think of it schematically like this. It says, if I have a relation and I want to prove that A and B stand in that relation, well, if I know that A and B are identical, and I know that R holds for any x of it with itself, then I can infer that R must hold for A and B. So that's roughly the schematic form of that rule for elimination. Okay, so now we're going to see how to interpret these things. Let's suppose we have an ascending sequence of identity types like this. We have the type A and two terms, and then we can build this identity type. And then we may have a proof here, Q, that A and B are identical. Now we may have another proof, P, that A and B are identical. These a priori don't have to be related to each other. So we can build the new identity type over this type of proofs that P and Q are identical. And this may have terms, it may have various different terms, and so on. So we get this ascending sequence of identity types of different order or dimension, as you want to think of it. And now here's the interpretation. I'll draw a little picture here. So we have the type A we're going to think of as a space, and then the terms A and B are going to be points of the space, and a proof that A is identical to B is going to be a path from A to B in the space. And another one, Q, is going to be another path from A to B. So that's the idea here. And now, what should be a proof that P and Q as proofs are identical? Well, that's going to be a homotopy from P to Q. And of course, there may be more than one such homotopy from P to Q, some beta out here, and those may or may not be related to each other by further homotopies. So that's the basic idea. The identity terms get interpreted as paths, respectively, homotopies. So that's the basic setup. Now, I haven't told you how to interpret dependent types. So how should we interpret a family like that of types? Well, if we look at the rules and what they tell us about families of types, in particular, the rules will imply this inference. So let's study that inference for a moment and see what it means. If I have my type here, A, and then I have my type B is varying over A, so I'm going to represent that as a kind of space that's indexed over the space A. And the idea is if I have a term here, A, of type A, then I look at the pre-image of that map, and that's the indexing projection. So this is my type B of A, is the fiber of this map over A. Good? And then I have another point here. What did I say? A and A naught and A1. So here's another one. Well, that's going to have another fiber here. So there's B of A1. And now if I have a path here, P, and a term up here, B, is this my rule of inference? Yeah, I think I'm spelling out the ingredients in that rule. Then what the rule tells me is I can find a corresponding thing over here that is, I think of as P acting on that B to give me something over here. So, and in fact, I can do this not only for a path acting on a point, I can do it for lifting the entire path, not just moving the point across, but I could actually lift the entire path across, and by a more subtle use of the rule, I could lift a whole homotopy and so on. So this is the notion, of course, of a fibration. So the conclusion is that I should interpret, topologically, I should interpret dependent types of this kind as continuous functions which have a certain path lifting property. That is, I'll use fibrations of spaces as the interpretation of those. Okay, so I'm going to continue the homotopy interpretation as follows. The dependent types will be fibrations. The fiber of such a thing over a point is just the dependent type at that element. The identity type itself, then, should be interpreted as a fibration over the square of A with itself. Well, the natural thing to take is the fibration of all paths in A. That's indexed by the two endpoints over A. So that will be the interpretation of the identity type. And then the fiber of the identity type over a pair of elements will be the space of all paths from A to B. So that finishes the homotopy interpretation. Oh, let me just point this out. Of course, the path space classifies homotopies between functions, right? If I have two functions, f and g, from some space into A, then a lift like this across the path space is the same thing as a homotopy from f to g. It's a family of paths between the values of the functions. And so under this following through the interpretation, what we find out is that terms of identity type correspond exactly to homotopies between their two projections. So that finishes the interpretation. So here's a summary. The interpretation works like this. There is a well-known interpretation of the lambda calculus into topology. It's probably fair to say that it's due to Dana Scott. Types are interpreted as spaces. Terms are interpreted as continuous functions. And computability, which after all is the same thing as lambda definability, is then interpreted as continuity. So that's one way of understanding this topological interpretation, is we're modeling the notion of computability by using continuity. Okay? And now what we're doing here is we're extending that from the simply typed lambda calculus for the experts in the audience to the dependently typed lambda calculus with identity types. We extend that topological interpretation using the following basic idea. A term of identity type is a path, and we just follow that through now, and that forces the dependent types to be fibrations, it forces the identity types to be path spaces, and it forces the terms of identity types to be homotopies. And that's one, I think, good way of understanding how this interpretation works. Now, of course, we don't actually use formally concrete spaces and homotopies. It's much more convenient to use the axiomatic framework of Quillen model categories, because it gives us, of course, a wide range of different models. It subsumes the classical case of spaces or simplicial sets, and it allows us to use some of the machinery that the category theorists have developed for proving things about logical systems and interpretations of them. So, for example, some of the things that we can prove right off the bat are these, that we have this sound interpretation, and by soundness is just what I said in the beginning, that if a formula is provable, then it's always true under the interpretation. So that's the first result. And then the next one is maybe a little more surprising. It turns out that if a formula is always true under the homotopy interpretation, it's actually provable in the type theory. So that's quite a strong statement. And I guess we could summarize the combination of these two results by saying that type theory is a sort of logic of homotopy, or at least it can be regarded as that if you want to. Provability in type theory corresponds to being true under this homotopical interpretation. Of course, I'm sweeping a lot of details under the carpet here. I'm just giving you a kind of high-level sketch. Yes, Vladimir?
Go ahead.
I would also maybe say homotopy of logic, not only logic of homotopy. It could be both.
Well, we'll see. Okay.
My question is about this two-hit result.
Which one?
The second result.
The completeness result.
Is it in the context of a type theory with there so many type variables, three type variables, and product and identity type?
No, it's for an arbitrary type theory with identity types.
Really an arbitrary type.
But no, well, you could have some basic types, you could have some type variables or not, or only primitive types.
But like, are they inductive types?
They don't have to be, but they can be. They're not required. All that's required is identity types. But then you get a weak factorization system. So that's the result, is you can get a weak factorization. Yeah, it's still there if you add more constructors. And in particular, if you add higher inductive types, you get a whole Quillen model structure. But for that, you need some more constructors. Otherwise, you just get a weak factorization system. Yes. Not without higher inductive types. Okay. So I said it's a kind of logic of homotopy, but one can reasonably ask now, how expressive is it? How much homotopy theory can you actually express in this system and do? What kinds of homotopical constructions, properties, facts can be expressed? So I'm going to give you one example quickly, and that's the fundamental group and the higher analogs. And I'll show that these are actually logical constructions within this logic, this type theoretic system. So let's go back to our system of identity terms here of various orders like this, and represent them like this, which I've done here on the chalkboard. So this is suggestive, right, of a higher dimensional category. These are the 0 cells, the 1 cells, the 2 cells, the 3 cells, and so on. So think of this as a kind of higher dimensional category, if you like. Now, just as in topology, if we look at only the terms of orders 0 and 1, right, the points and the paths in the space, if you like, then what we see is that in the type theory, these things bear the structure of a groupoid. That is to say, in virtue of the laws of identity, we get groupoid operations on these paths. So, for example, the reflexivity law of identity tells us that for each point A, there's a path from A to A. The symmetry property of identity tells us that for each path from A to B, there's another one from B back to A. The transitivity law tells us that given 2 paths, there's a composite from A to C, and so on. So that's what I mean by the structure of a groupoid. What about the groupoid laws that you would want those operations to satisfy? Well, let's look. The groupoid laws would require these equations to hold. If we interpret these equations, it turns out that just as in topology, they don't hold, but they do hold up to homotopy. That is, so let's take one example. Here, this inverse law. The inverse law says if I take P and I take its inverse and compose them, I should get the constant path on A. So here's A, here's P going to B. I make its inverse, I look at the constant path, and now it turns out that the composite here is not identical to the constant path, but there is a higher dimensional cell relating them, a homotopy from this composite down to this one. And the same thing holds for the other groupoid laws. And so what I get is a kind of higher dimensional groupoid up to homotopy, a globular set, that is, an infinite dimensional graph like this, of cells of all dimensions, which together bear the structure of a weak infinite dimensional groupoid as it's been defined in homotopy theory. So let me pause here to emphasize this fact. I think it's a noteworthy fact that this same mathematical structure has occurred independently 3 times in mathematics. Once in higher dimensional category theory, once in homotopy theory, and now here it is again in logic. And there's a kind of amazing coincidence, I think, between these occurrences of this same structure, namely this weak infinite dimensional groupoid. So here's the result. I'll read it out. The system of identity terms like this actually do form a weak infinite dimensional groupoid in the formal sense defined by the homotopy theorists. For example, the definition of Batanin is used in establishing this proof. So every type in the system has a weak, a fundamental infinity groupoid. And a way of thinking of this is that the fundamental groupoid of a space then is not just analogous to the one that comes up in type theory. It really is the one that comes up in type theory. It's a logical construction. You interpret the logical construction in spaces, and you get the fundamental groupoid of the space. Okay, now let's combine 2 things that we've talked about. On the one hand, the representation, I don't know which way the representation goes here. I would say constructive type theory in homotopy theory, but anyway, the presentation of homotopy theory in constructive type theory, if you like, with, on the other hand, the well-developed implementations of type theory in computational proof assistance like the Coq system. The Coq system can be used to actually check proofs and to find proofs, help you find proofs in type theory. And so if you formulate some homotopically meaningful statements in type theory, you can use the Coq system to prove things in homotopy theory. And this is actually a very active program of research at the moment here at the Institute in this Univalent Foundation special year. A number of people are involved in finding such proofs in homotopy theory. So, for example, Dan Licata, I think next week, will give you some examples of this, and he'll show you some machine code that shows that gives a formal proof checked by the Coq system that, what, pi 1 of S1 is the integers. So, and just last week, one of our students, Guillaume Brunerie, gave us a proof that all the pi k's of the SNs for k less than n are trivial, and this has also been implemented in the computer system. So we can get the computer to compute at least some very simple cases of homotopy groups of spheres. Okay, so here's my conclusion of this second part of the talk. Type theory, as I've tried to convince you, gives us a kind of logic of homotopy. The logical methods can capture a significant amount of homotopy theory, for example, fundamental groups. Some of this is already being formalized into the Coq system, and some new results in homotopy theory and also elementary mathematics and even more general foundations can be implemented in that way. And now I want to say a little bit about this fact that I mentioned before, that some logical concepts can be influenced by homotopical ideas and conversely. So the first example I want to give you of that is this idea of higher dimensional inductive types. This is work in progress by Peter Lumsdaine and Mike Schulman and some other people who are here. So here's the idea. In type theory, there is a kind of conventional or customary way of presenting certain free algebras by means of rules of inference, and they are called inductive types. Okay, I mean, the idea is you have some algebraic structure, and then you look at the freely generated algebras with that structure, and those are, in a sense, inductively generated by the operations applied to the basic elements. And the framework for presenting this in type theory is a fairly rigid schematic setup that always gives you the right answer and then is possible to compute with in a very systematic way. So let me just review that for the familiar case of the natural numbers, and then we're going to generalize the same thing to formulate the unit sphere as an inductive type in place of the natural numbers. Okay? So what is the type of the natural numbers regarded as an algebra? Well, it has one basic element, and then it has one endo map on it, right? One operation. So we state, and then it has the property of being free with respect to this structure. So we state that as a rule of inference called a recursion property, which looks like this. It says, if you give me any type and any distinguished element, right, corresponding to this, and then a map on that type, then you can conclude that there's a map from the natural numbers into that type. I call it the map determined by recursion on this data, A and F. And that map has the following property. If I apply the map to the 0 up here, I get the A. And if I compose the map with the successor function, I get the map itself composed with this F over here. So what this is saying is simply this map rec is a homomorphism of this algebraic structure, right? Taking the initial one to this other one. So we can also look at this more algebraically like this. I have the natural numbers with their selected structure. If you give me any other algebra with that structure, there's a map rec taking this one to that one and preserving the structure. And moreover, this map rec is unique with that property. It's the unique map from this one to that one that preserves the algebraic structure. So that's what is usually called recursion and what is specified by such an inductive rule of inference. So now I'm going to do the same thing for the unit circle. Get ready. This is a new idea. What is the unit circle? Well, we can give it an inductive specification like this. It has a point, a generating point, and on that point, there's a path from the point to itself. I'm using this wiggly arrow notation instead of this type theoretic notation just for fun, just because it's more suggestive. Okay? It's just more suggestive, I think, than writing P of id BB. It's a path from B to B. That's all I mean. That's all I mean. So this thing has this algebraic structure, a point of S and a point of the identity type over that B with itself, a loop. And now what I want to say is it's the free thing generated by that, a point and a loop. So how do I say it? Well, I just write down this same kind of rule of inference. If you give me any other type with a point and a loop, then there's a map from S into X determined by that recursion data such that, well, it's supposed to have this property. If I apply the map to the point, to the base point of the circle, I get the base point back out. If I apply it to the loop of the circle, I get this loop back out. And this map, yeah, so it acts on paths and it acts on points. So here's the same picture that I had before, except now instead of having an endo map here, I have this loop on the point, and the map takes this loop to that loop. So this says that it's weakly free in the sense that it's initial, it's weakly initial. How do I express the uniqueness? So the uniqueness is expressed, so one way would be to say, well, there's a map here, unique up to homotopy, but then I have to say, given the homotopy, any two homotopies themselves have a homotopy between them, and any two of those, and so on up. So really the best way to say it is the space of all homomorphisms of this type from here to here is a contractible space. So that's actually how we express it formally. Okay, so here's a sanity check. If I take that definition in that form, I put it into type theory because I can put inductive definitions into type theory, what I get is a space in type theory about which I can prove now that it has all the right fundamental groups. So it has the right homotopy type. So Mike Schulman has checked this. 1n or 2? 1n, sorry. Anyway, Mike Schulman has checked this, and the proof of this, so this tells us, at least up to homotopy type, that this thing really is the unit circle. It has the right homotopy type in the system, having formalized it using this inductive rule. And the proof is a beautiful combination, I think, of ideas from classical homotopy theory and constructive type theory, and then the whole thing has been implemented in the Cox system, so it can be verified automatically by the Cox system. And this is what Dan is going to talk about, what Dan is going to talk about next week. He'll give a survey of this proof and show the implementation. Yes? Yeah. Right, exactly. So I'm going to say it in a minute, but I'll just answer now. I can take, to make the fundamental group, I would take, so if I have my space here, x, and then a base point, a, then I can make id x, a, but really what that is that's the loop space of x at a. So what I need to do further is I need to take something like pi 0 of this thing, right, in order to actually get the fundamental group. And this is another construction that I would have to explain separately. But there is such a construction. Okay, just one more quick example. The unit interval, of course, can be also given as a higher inductive type. It just has a little more data. It has 2 points and a path between them, which is not anymore a loop, right? And then again, I give the same kind of inductive scheme, saying given any other type with 2 points and a path between them, there's a map from the interval into that space, taking the path to that path and unique up to homotopy. So here's a slogan. In conventional topology, we start with the interval and we use it to define the notion of a path. Here we've reversed the order of definitions. We start with a path as a primitive logical notion and we use it to define the interval. Okay, is that good? And now, using this same scheme of higher dimensional inductive types, we can do lots and lots of other things. Here's just a list of a few examples of the sorts of things that one can do. And this is certainly a topic of current research, ongoing research. What kinds of things can we do? So for example, here is the truncation, the pi 0 that you asked about. Here's the Quillen model structure that Vladimir asked about before, and so on. There are lots of things that one can do. Good? It's a type. Oh, sorry, for a given type, it's a quotient type. It will be the associated set of connected components of the other type. So it's another type. Pi 0 itself is going to be a functor on all the types, which takes arbitrary types and reflects them down into the types which are sets in the sense that Vladimir was talking about before. Set is a defined, well, it's a defined notion, as Vladimir was saying before. Among the types, and I'll get to this in a minute, that it turns out that among all the types of the system, there's a kind of stratification or hierarchy into different, what Vladimir has termed H levels. And these are logically definable classes of types. At the lowest level are the types which are contractible. Then there are the types which are either empty or contractible. Okay? These are the ones that, such that if you take any 2 points in the type and you look at the type of paths between them, that's contractible. Then you go up like that inductively. So the next level is the sets, right? The next level is the groupoids, 2 groupoids, 3, and so on. So these are Vladimir's H levels. And now the H level 0, 1, 2 is the level of sets. That's included among all the types, and pi 0 is a reflector going back into the level of sets. This is a notion which can be defined by an inductive construction in the same way that we defined the other ones. These inductive constructions, if you think about, let me just say one more sentence. These inductive constructions, if you look at them, I think I made it fairly clear in the schema there. It's a way of capturing a kind of universal property or universal mapping property. You say the inductive thing is the thing that has the universal property with respect to some other structure. So this reflection can also be, because it's a left adjoint to an inclusion, it can also be given by a kind of universal property, which can be stated then as an inductive rule of inference. So that's the idea. Well, I have a general rule which says something like, if I have a type A, if this is a type, then I can make pi 0 of A is a type. And then if A is a term of type A, then I can take some operation on it. Maybe I'll call it, pi 0 is not good, maybe I'll call it A like that, of type pi 0 of A. So that's a kind of rule operating on the terms. And then there will be an elimination rule which tells me what happens if I map from A into anything S which is known to be in pi 0, then that will correspond to a map from pi 0 of A into S, if I know that S is in pi 0. Yeah.
There is actually there is one approach to pi 0 which is pi negative. There is another approach to pi 0 through hash forward, as I call it, hash forward. That can be done
Oops.
conditionally to type theory. You can actually prove that pi 0 is conditionally constructed using some kind of predictive argument.
Yeah. Okay. So the conclusion that I want to make is this formal system now, with the addition of these higher inductive types, or even just with the interval, has a sort of intrinsic geometric content. So what do I mean by that? That's a pretty fancy thing to say. What I mean is, if we want to prove things about loops in a space, we don't start off, as you do in set theory, by first constructing the natural numbers, then the rationals, then the reals, then the Euclidean spaces, then continuous functions out of the paths, and so on, and build up all the machinery of homotopy theory in a kind of, how should we call it, analytic way, right? Instead, we put the geometric objects in right at the base by stating what their universal properties are, and then we reason directly about them in a kind of formal, axiomatic way from their basic universal properties. And that's what I mean by an intrinsic geometric content in this formal system. So it treats homotopy theory and related matters in a different way than the formal treatment in conventional set theoretic foundations. That's the point. Good. Univalence. Good. I have enough time. So I want to talk about the univalence axiom. The Univalent Foundations program is a new approach to the foundations of mathematics invented by Vladimir Voevodsky, which has this intrinsic geometric content that I was talking about, and at the same time, a computational implementation, which I also mentioned. And so these are two novel aspects of this approach to foundations that are not found in conventional foundations and which make it quite interesting. It applies not only to homotopy theory, but also subsumes set theory and formal logic in the way that I just explained, because among the types are, in particular, sets and propositions, and so you reason about these things in a uniform way in one system. Instead of saying there's logic and then inside the logic you formalize set theory or something like that. This is one system that treats everything together. Vladimir has proposed a new foundational axiom inside this system called the univalence axiom. And it's quite an interesting and powerful mode of reasoning that I want to explain to you now. It captures the informal mathematical practice of identifying isomorphic objects. So we all know how in everyday mathematics we have a kind of abuse of language or systematic sloppiness where we regard isomorphic things as the same, right? But we do it in a kind of informal way. It's not anything that's really permitted by the official foundations of mathematics. It's kind of an embarrassment that the official foundations of mathematics don't allow us to do that. We have to develop kind of conventions for doing that informally. And the idea behind the univalence axiom, or one way of understanding it, is that it formalizes that mode of reasoning according to which you can treat isomorphic things as being identical. So let's explain this. So first of all, what do we mean by isomorphism? So in type theory, we can formalize the usual notion of an isomorphism. An isomorphism between two types is a pair of maps back and forth such that the composites are identical to the identity function. So type theoretically, we would write it like this. Don't be alarmed here. I make the type here of isomorphisms from A to B. Let's work from the outside in. There are. So that's an existential quantifier. So that means there is an F from A to B. There is a G from B to A. Good. Here's a universal quantifier such that for all x in type A, G of f of x is identical to x. And for all y of type B, f of g of y is identical to y. Good? That's a perfectly, I think, perfectly natural reading of this informal statement. So now this then is a type of all isomorphisms from A to B. And in order to prove that A is isomorphic to B, what you do is you show that there's a term of this type. That is, you exhibit an isomorphism from A to B. So in a sense, we can identify this type of all isomorphisms with the statement that A and B are isomorphic. So here we have the statement that A is isomorphic to B. Here we have the type that A and B are isomorphic. In order to prove the statement, we exhibit an element of the type, which is then exactly an isomorphism from A to B. So that's this kind of propositions as types, Curry-Howard correspondence at work. Now, it turns out that it's convenient, for reasons related to what Vladimir mentioned, that only some types should really be treated as propositions, to add a further coherence condition relating the specific proofs that gfx is x and fgy is y. But I'm not going to put that in here because it just makes for a more complicated formula. But from now on, by isomorphism, I mean this together with this unstated coherence condition on those proofs. So that's what I mean by isomorphism. And once you put that in, then this notion of isomorphism under the homotopy interpretation becomes homotopy equivalence of spaces. It means maps back and forth, the composites of which are homotopic to the identity on each side. Yeah? It also subsumes the notion of logical equivalence, isomorphism of sets, categorical equivalence, two categorical equivalence, n categorical equivalence, and so on. So it's one notion, always written the same in the type theory, that subsumes all of these other notions. It's quite a remarkable invention. Okay, now let's look. In the type theory, by a definable property of a type, I just mean another type that has a type as a variable. It's something you can say about a type. And now it turns out that all definable properties in the type theory respect type isomorphism in this sense. If I have two types which are isomorphic, and I can prove this thing of one of the types, then I can also prove it of the other type. I'm speaking very schematically now, just to kind of give a rough idea of what's going on. So all definable properties respect type isomorphism, and in that sense, they're invariant with respect to type isomorphisms. It's a basic property of the system that you have to prove. It requires some doing to show that the system has this property. Zermelo-Fraenkel set theory, for example, does not have this property. It's a special feature of type theory that it is invariant in this sense. Conventional set theory of Zermelo-Fraenkel does not have this property, but the type theory does have this property. So now what I've said here is a kind of indiscernibility statement, right? It's saying for every property, if it holds of A, then it holds of B. So this is kind of like Leibniz's definition of identity, isn't it? It's saying P of A implies P of B for all P. How do we compare? Let's compare this notion with the notion of identity of types. Okay? How do you express identity of types? Well, in the system so far that I've mentioned, you can't really talk about identity of types. But we can extend the type theory with a new constructor called a universe, and then on the universe there will be an identity type, and that's how we can talk about identity of types. We say two types are identical means they stand in the identity relation on the universe that contains them. We add the universe and we add a way of reasoning about types as being in a universe, and then this gives us a way of talking about identity of types, which we couldn't do before. So now it's easy to construct a comparison map between this identity type and the type of isomorphisms, simply because if two things are identical, well, the identity is itself an isomorphism, and then you get an isomorphism there. So of course identity implies isomorphism, so that's easy to do. And now hold on to this map right here, this comparison map between identity and isomorphism. The univalence axiom says that that map is itself an isomorphism. So you could read it saying this. You could say identity is isomorphic to isomorphism. Good? That's the univalence axiom. Let's talk about some consequences of the univalence axiom. So the first consequence is this. Because that thing was an isomorphism, there's a map coming back. That tells us that isomorphic objects are identical. Right? If I have two objects, I can prove that they're isomorphic, then I can find an identity relating them. The system with this univalence axiom and a universe still has this invariance property. Anything you can prove about one type holds also of any isomorphic type. And in fact, you can formulate the univalence axiom itself as saying that this invariance property holds for every type in the system with respect to isomorphism. So that's a good way, I think. Pardon me?
Is that an equivalent formulation?
I think that is an equivalent formulation. If you do it carefully enough. I mean, this is a very schematic presentation. You'd have to do it carefully enough, but yes. Right, I mean, put in here A is identical to B. Right? And if A is identical to A.
You can have A identical to A.
Exactly, and then you get A is identical to B down here. So, although this is incompatible with set theory, conventional set theory, it is consistent with the type theory. And the proof of that is a construction due to Vladimir of a model of type theory in consimplicial sets. So, in the consimplicial sets, there is a universe, which is a concomplex. It has a universal confibration over it, which is univalent in the sense that it satisfies this condition. And maybe if I finish in just a moment, we can have Vladimir explain why it's called univalent. Now, I praised the computational character of this system, and I said that the implementation in the proof assistance depends, in a sense, on this constructive character. But now we've thrown in a new axiom, so we have to be careful to preserve that. We don't know yet, but we have a sketch of a proof or a conjecture due to Vladimir that adding the univalence axiom does preserve the computational character of the system, and that is one of the topics that is under active investigation right now during this special year. Okay, so here's the conclusion. We have this homotopical interpretation of constructive type theory. It allows us to reason formally about homotopy theory. We have a new approach to the foundations of mathematics based on that, with intrinsic geometric content and a computational implementation. And we have a new foundational axiom, which is a powerful principle of reasoning. And hopefully, it also has a good computational character. That's my conclusion, and here's where you can go for some more information. If you want to keep up on what's going on here, the weekly talks and schedule and so on, that's here, and then here's some more general information. Thank you very much.